to continue with that list, finish it, and start off on wind if possible. So today is 21st of September 2023. Sorry. So we're continuing with this list. I know we were numbering these items, so this should be number 3. 2, 3, like that. Okay. And then number 4. Is a structural system that is generally referred to as a tube-in-tube. In this system, you have generally a central core or centrally placed reinforced concrete solid wall core, and then it is surrounded by columns. It's referred to as a tube-in-tube. For example, so let me just write here. This constitutes a central reinforced concrete core surrounded by external columns, preferably on the perimeter of the building. Preferably on the perimeter of the building. Okay, so basically what you would have is you'd have, for example, if we just took a very simple layout of a building. A very simple layout of a building. Of course, you would have the external columns. So you'd have columns there. Of external columns. Later on, you'll understand a bit better why this system would be a bit stiffer, more stiffer than just having shear walls. It's basically shear walls that form a tube. So then you would have some form of reinforced concrete, tube, preferably centrally placed in there. So this is reinforced concrete tube, and then reinforced concrete columns forming an external tube. Internal tube. Internal tube. So you have that core, and then there's a ring of columns, so it forms something like a tube in tube. That's why it's referred to as a tube in tube. Okay, the last one, and I'll show you a real life example of this shortly. Let me just highlight the last one, so that when I show you this example, you see all of it. So now, if you have a tube in tube building, and maybe the height has become too much and it's swaying too much. you could actually have something they call or they refer to as an outrigger system. Where if you have, for example, a building like this, you got a tall building, you've got many floors. Many floors of this building. If it's swaying too much, and in plan, let's say it looks like just what we had sketched up here. So again, you had your columns, just as we did in this other, this tube in tube. So you have a tube in tube structure. And of course, you have a central core. Now, if this building, you find that because of the height, it's swaying too much, it is possible to now incorporate as part of the structural system walls that go from the central, or deep beams that go from the central core to the external columns in that manner. It's possible to do that for some floors of the building at some interval. Okay, so you would call these outrigger walls. And then what you do is, for example, this building, if it was 100 stories, let's just say for the sake of, or let's say 60 stories. Okay, so we would take, for example, after the first 20 or 25 stories, we would have a floor where we would have this system. Then another 20 stories or something, we would have a floor that would have this system of walls. And then another 20 stories like that, or 25, we would have another floor that has got this kind of system. These walls are basically like deep beams that are transferring the shear from the central core to the external walls. And what exactly, the way it does this is similar to the outrigger boats. You know, the small boat that has got a piece of pole that is that goes across, and it has a sail, and this pole has got some timber planks there. Okay, and what it does is that it is these poles, this pole and those planks that give the boat stability. When it wants to topple, these ones are floating this side, these ones are floating this side. So this building, when it wants to sway, the very deep elements, which are walls basically, that are moving, that are connecting the central core to the external columns, what they do is they sort of stabilize the building, so they reduce the sway significantly. Okay, so that is called an outrigger system. Usually what happens is that you would put this system in the floors that are referred to as service floors. So these would be service floors. I'll explain what that is. When you design a tall building, say beyond 25 stories, you start having a need to have some floors that are just for services like water pumps, like water tanks, like compressors for ventilation and things like that at different intervals, because it might be difficult and inefficient to pump water, say up, say a 60-story or 100-story building. So the water will be pumped up in stages. It is the same thing with the wastewater. If you allowed wastewater to just flow from the top of such a tall building to the bottom, then you know you'll have a problem with your fittings because they will just break. The pressure in the pipes would be so immense that you will not be able to get taps that are able to then hold the pressure in the first place. So because of that, the heights are broken and the services are therefore provided for a certain number of floors, then another certain number of floors, like that, and it makes it easier for mechanical and electrical services to be put in. That's why they're called service floors. Now, these service floors, they are not usually occupied or not designed to be occupied by human beings. They are only spaces for equipment, like water tanks, etc., etc. So you can easily throw in walls in this manner that we have shown here, without having to have provisions for movement of people or spaces for lighting or what. So that's an outrigger system. Now, if you allow me, I will open. I'll show you how this one looks like in a real life project. So this is inner core. So just give me a minute. I see if I can retrieve the drawings, or at least a write-up for this thing I show you. Okay. So I found an image here. Perfect. Let me try and share this image. Yeah, this one. Share. So what you have here is an image of a fairly tall building that was basically a tube in tube. It was a tube in tube. So you have a central core. You have a central core here, which is elaborate, it's curves, but it's basically lifts. These are lift rooms and staircases and stuff like that. So it's a massive central core. And then externally to that, what you see as blue, they're actually composite columns made of concrete and steel. I don't know whether you can see that. So there's steel section within the concrete column. So they're heavy, huge columns, composite, that are an external. So initially a tube in tube. Then in analysis, we found that this building was swaying too much. So we picked a few floors and made them into this system, which we call an outrigger system. Let me see if I can find. I know there was some write-ups that were nicely showing. This is yes. So let me stop sharing that. I show you. Share this one. Okay, so this shows an extract of. So what am I sharing now? Yeah, that's what you're seeing, eh? Okay, good. So this shows an extract of how the building looked like, the core and the outrigger system. So you have a few floors from below, maybe almost 20, there was a service floor, so we put an outrigger system there, and then another few floors above, another service floor, we put an outrigger system there, and another floor, and almost at the top, we also put an outrigger system. So what I was showing you, yeah, this figure here is a blow up of one of those floors, service floors, where we put an outrigger system, and that's how it looks like. So I've shown you both a tube in tube. So this building was a tube in tube. There were external columns, and then an internal core, and then I've shown you also the outrigger system. Okay, great. So now with that bit, I want to close that part of this discussion. This is Elvis is raising a hand. Yes, Elvis, please, you can go ahead. And I said, if you have a question, just switch on your mic. You don't need to raise your hand or whatnot. If I don't see your raised hand, then you miss the opportunity to say, yeah. So please, you just switch on your mic and talk. Oh, okay. So his mic is not. In the tube-in-tube system, the core, can it be like a somewhat hollow RC structure running from top to bottom of a structure that is most Kenyan-built structures? Lifts are located there. Actually, the core is usually used as a lift core. So you take advantage of the need to put the lifts, and you use that as a core. In fact, this is when we talk about when we talk a bit about shear walls, because we'll talk shear walls in this course. We will also talk about the location of the shear walls, and once you have a bit of an understanding of what we need in a shear wall, you'll agree with me that that if when you place it centrally, then it stiffens the building the best, and you don't have problems like twisting of the building and stuff like that, which I'm hoping you will see in the assignment, in the buildings that you have chosen. Okay. So yes, the core is usually a hollow element, with reinforced concrete walls, just like a lift core. The building I've shown you, the core, that's where all the lifts were, and there were many, because it's a very tall building. So there are many lifts in there, dedicated for different sections of the building. Okay. So you're right that that is what. Anybody else with a thought or a question or a comment before we proceed? Good. Okay. So now I want us to move and start talking about. I want us to now move and talk about what? Wind loads. Okay. I want us. I want us to, on these wind loads, I want us to pick a hypothetical building. So I will sketch here a small building, hypothetical, that we can work on in these discussions. So let's assume that we have a building like that.
Excuse me.
Yes, please.
We can't see your screen.
I've not shared. Okay, let me just share. Here. So I'm just sketching some simple rectangular building that I want us to use for the discussion of these lateral loads. Okay, so 1, 2, 3, 4, 5. Let's see. Side, let's have 3. That's a bad line. Let's assume that this building has got dimensions this side of 5 meters. 5 meters this side. 5 meters. 5 meters. Let's assume that this side we have dimensions of 7 meters. So that's 7 meters. 7 meters. Let me write the numbers with slightly deeper pen. They're clearer. So here we're saying let's have 7 meters. 7 meters, 7 meters, 7 meters. And here let's have 5 meters. Okay. Let's assume that this building has got columns at each of the points where the grid lines are meeting. It's a very regular building, very straightforward. Let's assume it's looking like that. So we'll use this to just out of interest, did you find this architectural drawing that I was asking you to find? Hello? Ladies and gentlemen, did you find the drawing I asked you to look for?
Not yet.
No, you haven't, eh? Okay, so I am thinking if that is becoming too difficult, we could work on this, a similar building like this. Have you formed the groups? Because I asked the class rep to form the groups and send to me. He hasn't done that.
I will send you, sir.
Okay, so I think, so let's remove the headache of looking for that drawing. Let's discuss this hypothetical building. I will tell you what each group will do in terms of dimensions of this building, but let's work on this hypothetical building. Okay. We are how many groups? We said we make 6 groups?
6 months.
Yes, sir.
And just 6 months.
Oh.
Muiga, we can hear you. What are you saying? Mutero. Oh, he's now switched off. Sorry. So, fortunately, we had started a discussion on wind loading with the other in the other class. So here we will push that discussion a bit further, and we hope that in the other class, the other group also will be able to mention some important things that are relevant to the low-rise structures. So let's also assume that this building has got in elevation, it looks like this. What do I use? Let's assume in elevation, this building looks like this. we'll also discuss later how you'd support the columns at the bottom. Okay, let's just get it right here. Let's draw it right. So usually we would pin the columns. In this course, we will discuss why we would pin them and not fix them. We'll pin the columns for such a building. Let's assume that this building is bad line. Let's assume that this building let's make it really tall, though it is slender. Make it really tall. So say 18. Assume 18 each 3 meters. Or to floor height. Let's assume those stories are 18. So if we assume that, then what is the total height of this building? What's the total height? Is 18 by 3. 30, 54. 18 by 3, 54. This thing is 54 meters tall. 54 meters tall. Okay. And of course, we have the lateral dimension, which is basically 555. It's a lateral dimension here. It is 5 meters from one column to the other. It's 15 meters. Three each 5 meters. Okay. So in reinforced concrete design, one would do something we call preliminary design to decide what type of elements to use and what sizes of those elements to use. So because this unit is not reinforced concrete design, we will not go into the details of those. I will just give you sizes to assume that these sizes have been determined from preliminary design of the building. So you have done the preliminary design and you have the sizes. From what we discussed in the other unit, we did say, for example, if this building was in Nairobi, then site is in Nairobi. Outskirts, not city center. Then basic wind speed, and we'll open this standard shortly, is 28 meters per second. Sorry. Per second. Let's assume that the columns on this building are 800 by 800. Once we do the design, if they're not working, we will change them. Let's assume columns 800 by 800 millimeters. Assume that the beams are 500 deep by 200 wide. Let's assume that the slabs are all 175 millimeters thick, solid slab. Assume that the partitions, this building, are in the range of 2.0 kilonewtons per meter square. Okay, so we got here the plan of the building. Here we got the elevation of the building. Now I want us to open this standard we're looking at so that then we proceed and calculate the wind forces on this building. So you remember we did say that there's many standards that are dealing with oh, that's a newer one. I want to refer to the very old one. It's the easiest to understand. There are many standards that deal with wind, but there's this this standard that I had started taking you through in the other class, and hopefully we will catch up with the rest of the team, or they will catch up with us when next time we meet. This standard deals with wind, and the newer, more modern standards, they tend to have a lot of similarity with this standard, only that they are a bit more refined. And I did mention that as we go along, I will mention to you what the refinements are in the relatively newer standards. Now, we did say that for us to calculate the wind force, and this I'm doing as a recap very quickly, for us to calculate the wind force on a building, we first need to determine or to know the speed of the wind, the prevailing wind speed of the area. And we said that this wind speed, prevailing wind speed, is usually derived from meteorological data and statistics. So they collect the data and then they do statistics to say, so generally this area you can use this kind of wind speed. Now that wind speed, which is our starting point, we said it's referred to as a basic wind speed and is denoted in this standard, or by this standard, as uppercase V. Then we said, so for example, in Nairobi, the number that we have used, this wind speed that we've used, has been 28 meters per second. Now that applies for the whole large area where Nairobi sits. So then we say, what if the sites have got different conditions in terms of how exposed they are, etc., etc. So then we say that there is need to make the basic wind speed into a site-specific wind speed referred to as a design wind speed. I'll repeat. There is need to make the basic wind speed, which is an overall number that has been provided, into a site-specific wind speed. And that site-specific wind speed is what is called design wind speed, is the wind speed that eventually we use to design for the wind force on the building. To achieve that, we need to put in some factors into this basic wind speed so that it can become a site-specific wind speed. And we said for this standard, there are three factors: S1, S2, S3. We had also started looking at those factors. Maybe I can make this a bit bigger so that we can read easier. We had started looking at those factors, and we saw that the factor S1 is a topography factor. It deals with the topography of the land. So whether land is flat or it's hilly, so whether the building is on the valley or at the top of the hill. So this factor would take care of that. And then we had also started looking at the factor S2, which deals with three items. The factor S2 deals with three items: ground roughness, building size, and height above ground. We had started talking about that. We looked at the ground roughness and we saw that this standard proposes 4 different ground roughnesses. Now, this kind of ground roughness classification you'll find in the Eurocode, you'll find in the BS 6399, which is now also obsolete, but it was newer to this standard. You'll find this in the American standard for loads. I'm forgetting the code, is ASC something. If you pick that standard, you'll see this kind of classification for ground roughness. Basically says if the ground is very open, then it's more critical than if the ground has got large, numerous obstructions, which in this case would be categorized as ground roughness number 4. So we had looked at that, and we had said that the size of the building affects the maximum average wind speed that the building can experience. I'll repeat. We said that the size of the building affects the maximum average wind speed that the building can experience. And as the building becomes bigger, the maximum possible average wind speed that the building can or will experience becomes lower because of the averaging effect. As the building becomes smaller, the maximum possible wind velocity becomes higher, and this size, as it becomes smaller, this concept goes all the way to be applied to fittings. Okay, so cladding, glazing, roofing, intermediate fixings, etc., etc. So this is, I think, where we had stopped in the other class, and I want to pick a little bit of discussion on this. So consider this small thing that we build, Ushago. So you got a small house here you've built. You got a small house here. Small house. That's a bad line. It's a small house. Okay. Got a nice door there. Maybe you got a window. Got another window there. etc., etc. So there's wind that is prevailing in this area where you've built. And we know generally that we would fix the mabati. You go to your mabati there. You can even label it. Now let's use a brighter color so that it stands out. Go to your mabati there. And I'm asking a question. How do you determine the number of nails required to effectively hold this mabati? In place. I'm asking a question, and I'm opening this to the class to give ideas. So, ladies and gentlemen, you're doing your mabati uko kwa village, and you want to tell the fundi, ensure you put this number of mabati, this number of nails for each mabati, 3 nails for each mabati, or 4 nails for each mabati. How do you determine that? Food for thought, or maybe food for discussion. Ladies and gentlemen, tell me your thoughts.
Okay, my thinking is about the length of the mabati. You determine the number of nails.
So John Masharia thinks that the length of the mabati would determine the number of nails. Okay, we have heard you, sir. Anybody with a different thought, or anybody wants to contribute to that thought? Thank you, John.
I think it's considering the forces from the wind, and so the number of nails will determine how firm the mabati will be. Because if the wind force is too much, it can pluck off the mabati. So as to hold the mabati more, somebody may opt to use more nails so that the mabati is held firmly.
Correct. I think you're both right. The answer I was looking for is what Bill is saying, but in the thought that Bill is sharing, the length of the mabati would come into play. So let's go back to this standard. If we were to decide on the number of nails that we need to hold the mabati down, we would need to think of the mabati as a cladding element. Okay? And then we would couple the wind speed and the pressure and say, if the prevailing winds in this area are this much, how much pressure would generate within the building? Okay, and I will take you through that as well, so that you see how those pressures are calculated. Then that pressure is what we would want to make the mabati piece to fly away. Okay, so the mabati piece, the dimensions of the mabati piece, including the length that John mentioned, and the pressure gives us a force. Then we now would ask, one nail, how much force can it hold? Then we say, so we need to put this number of nails to hold the mabati. Now, here in our country, we do not have a problem of too much wind. We do not have a problem with too much wind. But elsewhere in the world, they experience extreme winds again and again. And what happens is that if you have watched the videos of places where these winds have occurred, and nowadays we live in a very good age that you know, everybody has got a video camera in their phone. So as it happens, you find somebody has shot a video and shared it maybe on some platform. You'll notice that as the wind comes into the area of the building, whether it is real life videos or even in movies, it is the cladding that first peels off, courtesy of the pressure that the wind exerts on the surface of the building. The cladding that goes off. I'm sure you have also seen that when they get in some places in some areas in the world, when they get an alert that there will be these very high velocity winds, what they do is they board their windows. You know, they hammer timber planks to cover their windows from outside, so that the wind will not suck out the glass panes, because the glass panes are weak. Okay, so if you were to design, for example, a window that is resistant to this kind of winds, then the glass itself would need to be analyzed against the amount of force that it would experience. And for you to get that amount of force, the wind speed that you would need to calculate would be calculated against class A of the size of the building. Class A, you classify that as class A of the building size. And that will be eventually captured under the factor, site-specific factor S2. The site-specific factor S2 deals with ground roughness, which we've talked about. We talked about in a previous session. The building size, which we are talking about now, okay? So for you to do that, for example, so they tell you, engineer, we have this we built this very nice home overlooking the beach. And we've put huge window, you know, the whole wall is just a window. So we want to put glass here, maybe sliding glass door. And we don't want any grill, and we don't want to shut this with some steel shutters or anything. We just want it to be that way. So if there's heavy winds, we just close it shut, and we can leave it open. We look at the rain as it falls, or we can put curtains or something like that. So if you were to design that, then you would categorize that element under all units of cladding, class A. And you will see that this is the most critical class of for the wind speed. Then if you are considering buildings whose dimensions, either horizontal or vertical, does not exceed 50 meters, you would classify that as a building size class B. If the building that you're considering has got a dimension, either vertical or horizontal, which exceeds 50 meters, then that would qualify to be categorized as class C. So now if you look at our building, the height is 54 meters. The horizontal dimension, one side is 15, the other side is 35. But on account of the height, which is 54 meters, then this building, when we are considering the wind on the whole building, then it would fall under class C. I hope what I'm saying makes sense. Now, I'm coming back to the cladding units, because this is something that we don't usually, you find a lot of engineers don't bother to check. Okay, so rule of thumb, but you find the extreme cases, like when you have to really design those very luxury homes. So the glass panel that will go into that window would be a structural element able to resist the pressure that you have calculated. So you check it in bending and specify adequately, adequate thickness and maybe adequate lamination for this glass to be able to resist the pressure that you will have calculated from whatever wind speed that you'll have derived. Then the frame of this glass would also be a structural element. So you need to design the frame of this glass to be able to transfer the force of the wind from the glass to the rest of the building. So the frame would become a structural element. And then the part of the building where this frame would be mounted would also be a structural element that you need to check. So you wouldn't want to fix a frame like that onto masonry, because masonry might not be a good anchorage for this kind of requirement. Okay, so that's cladding size. And just to remind you, this factor S2 takes care of three items: ground roughness, building size, and height above ground. So we have talked about the height above ground. Generally, wind speed if this was wind speed, no, if this was height above ground, sorry, this was height above ground, and this was wind speed, the variation is like this. Sorry. So as you go up above ground, the wind speed increases, and it keeps increasing until at some height above ground, it doesn't increase anymore. It becomes constant. So if you go beyond that, you still find the same wind speed. It's a general trend. It doesn't have to be exactly correct that way, but most wind design standards for buildings, this is what they suggest. So this standard that we are looking at does not have this curve, but if you pick the newer standards like the BS 62399, or if you pick the Eurocode for wind loading, if you pick the American standard for wind loading, they actually present a curve like this to say this is how generally the wind would behave with height. So why is this important? If you're designing a building if you're designing, say a building, let's say it's 20 stories, sorry, 20 meters, let's say, no, 50 meters, let's say, 50 meters, like our building, okay? The wind speed here will not be the same as the wind speed here, and will not be the same as the wind speed here because of this variation. And the factor that takes care of this variation from one floor to the other of the wind speed is still the factor S2. And that's what is referred to as height above ground. So we said three things. One, ground roughness is catered for in S2. Two, building size is catered for in S2. And three, height above ground is also catered for in S2. Now, with that mention, then let's look at how this standard gives us values of S2. Then we will, or maybe we can talk briefly about S3, and then we come back to this table. Let's just see what S3 is, and then we'll come to this table and we see if we can make sense of it. S3 is a factor based on statistical concepts given in Appendix C. So there's an Appendix C in this standard for that. But generally this factor is adequate to assume it as 1. And what the statistical concept is that it takes into account a concept that we will talk about to some bit more extent in terms of earthquakes. It takes this takes into account, let me use a different pen here. It takes into account the degree of security required and the period of time in years during which there will be exposure to wind. When we discuss earthquake loading, we will talk a bit about this item here, degree of security. Okay, so for now, I will not go into it very much. We will cover it a bit to a bit more detail, but it is adequate for our discussion in this class to know that it is sufficient to assume S3 to be equal to 1. Okay, without going into too much detail. So now, this S3 is an easy one. What I want us to look at is the S2. And S2, the values for S2 are given in this table 3. So this table 3 gives us the values of the factor S2. And it combines the three considerations: ground roughness, which was the first consideration; the building size, which was the second consideration; and the height above ground, which was the third consideration. If you will remember, we just concluded on this discussion. Now, for the ground roughness, you remember we had 4 categories: open country with no obstructions, open country with scattered windbreaks, country with windbreaks, and what would mimic a city center. Okay, so the ground roughness is catered for in these 4 broad columns. Under each column of these, there is the class of the building size. Under each of these 4 broad columns is the classes A, B, C. So if for example, you're putting up a building or designing for a building in open country, you would pick this column and then come down and say, so the building is in an open country, so what's the size of the building or element that I'm dealing with? So for example, if our building was, say, in Syokimau, next to the airport, so it would qualify to be under category A of ground roughness. Okay, and then we would go on and classify it as class C. We have seen is class C. Why is it class C? Because it's one of its dimensions is greater than 50 meters. Okay, So we have, up to that point, dealt with two considerations: ground roughness and building size. So we know that we need to read off this column. And then now we will go and say, so this level here is 3 meters. This is 3 meters. This is 6 meters. This is 9 meters, because each of them is 3 meters floor to floor. So we'll come and read off an S2 value for 3 meters, then read off an S2 value for 9 meters, for 12 meters, for 15 meters, for 18 meters, for 21 meters, and so on and so forth. So the S2 value per floor will change, courtesy of the height of the building above the ground. I hope that makes sense. Okay? Up to that point, anybody with any question or clarification before we move to the next item? Okay, great. So now, let's go ahead and make an attempt to calculate the wind force on this hypothetical building. This hypothetical building. So we've got the basic wind speed. We've got the basic wind speed. Let me write here, therefore, calculating the wind speed, therefore, so we have, the starting point was a basic wind speed, as we had said previously. So basic wind speed V is 28 meters per second. So to calculate the design wind speed, we know that this standard, we are using CP3, yeah? CP, not CB, CP3, CP3, CP3. Okay. So we have, oh, sorry. So we got a blackout this side. But the genset has come on. Ah, perfect. Good. So we said we take the basic wind speed and we multiply it with the site-specific factors so that we get a design wind speed. Let's assume for this discussion that this value, we will assume it to be 1.0. And this value here, let's also assume it to be 1.0. So that we are only left with S2 to determine. And so that you can remember in your revision that this factor deals with the ground roughness, the building size, sorry, and the height above ground. Sorry. From this standard that we were referring to, once we have the design wind speed, we can calculate the dynamic pressure of wind using this equation. Once we have the design wind speed Vs, we can calculate the dynamic pressure of the wind denoted as Q. So let's write it here as well. Pressure due to wind is denoted Q. Q from this standard given as KVS squared, basically just a square of the design wind speed, which is site specific, multiplied by a factor. In this standard, or for this standard, K is given as to be 0.613. Therefore, Q is 0.613 multiplied by, I can remove the multiplication, Vs squared. And this will be in newtons per meter squared. It's a pressure quantity, yeah? So it's force over area. So it will, you get this value in newtons per meter squared. So then we go ahead and now read off the values from this table that we were looking at. Okay, so we are 12 minutes to completion, and I would like to, this next thing I wanted to show you might take a little bit more time. I'm suggesting that we pause here for this session, and we continue in the coming week, God willing. Okay, any question? Anybody with a question or a comment or a suggestion?
I have a quick question.
Yes, please. This is Masharia. Please proceed.
Okay, since you said that the S2 will be checking against the height.
Correct.
So at the end, will we add all the values and find an average, or what will we do?
No. I think that's a good question. This is what that's the point where I've stopped. What will happen is that eventually, you see, like the building like this, we call it U block. Each floor will have a different force for wind, which we will apply at every floor. So first floor will have a certain wind force that will apply at that level. When we go to the next floor, the wind force will be slightly different, and we'll apply that force at that floor, like that for all levels. This is what we need to do in a table, and that's why I've said the next step might take slightly more time than the 10 minutes. If we try to go through it, we'll rush through it, and then we'll not do justice to it. So I want to start with that when we meet next time. So each floor will have a different value, and we will not do an average. We will load those forces as they are onto the building. Any other question? Great. So thank you very much. Have a good morning, and we meet again in the coming week. Thank you.